thank you very much, everyone, for your patience and for waiting. Today we have a special guest, Stefan Dietze, who is a full professor for data and knowledge engineering at Heinrich Heine University Düsseldorf. And he's also scientific director of the Department Knowledge Technologies for the Social Sciences at GESIS, which is Leibniz Institute for the Social Sciences in Cologne. He is also a deputy director at the Heine Center for Artificial Intelligence and Data Science at the Heinrich Heine University in Düsseldorf. And also he's affiliated with the L3S Research Center in Hanover and the Düsseldorf Institute for Internet and Democracy. So there's a lot. And his research is at an intersection of natural language processing, information retrieval, and machine learning. Specifically, it's aimed at developing AI-based methods for mining and understanding large volumes of data, such as, for example, data mined from the web and social media platforms and their applications in the social sciences. And today, Stefan will talk about social scientific data quality and reproducibility in the AI era, challenges and pathways. And without further ado, I would like to give the floor to our guest.
Yeah, thanks a lot for the very nice introduction and for the invitation to the colloquium here today. Give me a second. I try to, yeah, I have to share my slides, so I remove yours. All right, so slides should be visible, right?
We don't see your
Not
slide.
yet.
They are not. Okay, let's try again. How does it look now?
Now it works. Now we see your slides. Perfect.
All right, super. All right, yeah. So I think I said already most things that have to be said to kick off the presentation. Just to say a few words. So I'm computer scientist by training, and the talk I'm going to give today is to some extent going to talk about the kind of challenges, opportunities, and to a large extent also challenges, the shift towards AI, deep learning based techniques and methods in the social sciences brings to those communities, and to that extent, or to a large extent, to the computational social science community. So it's a bit in between these two worlds. And yeah, to a large extent, of course, it's going to address very fundamental computer science and AI problems and challenges that have emerged as, I believe, very urgent kind of topics in the previous years when it comes to using state-of-the-art computer science techniques in research. So for those not that familiar with the social sciences, just to say that what we've seen in the social sciences is that, yeah, people have been turning their attention a lot to new forms of data, right? So specifically data sourced from the web, but also sensor data and data coming from mobile devices and the like. And to some extent, that has been transforming the social sciences, but also spawned entirely new research fields, such as the computational social science area, where both methods and data are, yeah, to a large extent different to what social scientists have been using in the past. And when I talk about new forms of data, to a large extent, I'm going to talk about things that we call behavioral web data. So things like online discourse as it happens on social media, online news, social web activity streams such as posts, shares, likes, and the like. Web search behavior is a very useful source of data and information like browsing, navigation patterns, search engine interactions, and the like. But also low-level behavioral traces such as scrolling behavior, mouse movements, also gaze behavior. We also work with EEG data. So this whole range of things is something people use in order to understand social interactions, cognitive stages of people, and the like. And what I think is specific about that is that this is data that's generally very close to users. To that extent, also close to their personal and potentially sensitive information. And it's also, yeah, very large and heterogeneous. And that next slide is something some people may have seen already, right? So that comes out every year, where some people try to summarize what happens on the web in 1 minute, just to give you a bit of an idea of what the scale of things are when you work with that kind of data. So, for instance, on X, people share 360,000 tweets. In 1 minute, we see 6 million Google searches happening in 1 minute. Roughly 7,000 prompts being sent to ChatGPT. That has become, of course, a very important kind of data source as well. And so there's lots of potentially sensitive, but also, yeah, very heterogeneous and very quickly evolving kind of data we're looking at. And um, so when people work with this kind of data, there's a wide range of techniques that are used in the social sciences, right? So people have been using traditional time series analysis methods, methods for network or graph analysis, dictionary-based methods, for instance, for sentiment analysis, and tailored machine learning models that were trained from scratch. So all these things have been happening since many years, of course, but also more recently, people, of course, turn to adopting transformer-based language models, whether that's open source models like BERT or pre-trained proprietary large language models like GPT or ChatGPT. And when I'm going to talk about AI in the remaining parts of the presentation, that's basically these last 3 bullet points. That's what I'm referring to. That's a very strong simplification, of course, but most likely if people mention AI in that context, they usually talk about any of these things. And there are, of course, very substantial differences with respect to scalability, robustness, efficiency, transparency or interpretability or reproducibility of all of those kind of methods. And that's to a large extent topics I'd like to discuss today as well. People have also been using AI on the one hand for they're using these methods for building data science and data analysis pipelines, but people have been using AI and specifically LLMs in many different ways, of course, in the previous years, right? So in the social sciences, LLMs have become very popular for simulating human behavior. And one kind of experiment people have been doing that has been done in many different ways and different flavors in order to investigate those kind of correlations was to compare the responses of language models with responses of survey participants in large survey programs, right? So if you look at that kind of prompt on the left side, was a question about gun violence and gun laws, and you get some kind of log probabilities from the language model back, and you can, of course, compare those with opinion distributions that came out of large survey programs. And really, as I said, that's been a very popular area of research, and specifically in that paper and in many other papers, people have been trying to understand the kind of biases models have, right? So if you look at, for instance, how different model responses correlate with specific demographic characteristics or specific demographic groups. In that table here, you see each column basically represents different models, and each row represents different income groups. And there you see that some models tend to correlate stronger with low income groups. Some models tend to correlate stronger with high income groups. Those patterns are also not very consistent across different kinds of topics and questions. They're just there, and they of course differ also if you compare any other kind of demographic features, whether that's political leaning or age or whatnot, right? So models have very unpredictable biases in that direction. And what people also have been doing a lot was working with personas, right? So trying to steer models in the direction of a certain kind of demographic by saying, pretend to be a low income, middle-aged person from Iowa or something. And then the expectation is that model responses get steered towards certain kind of demographics. And in that plot, you see that that steering works to some extent, right? So every data point here above the line basically has been shifting responses towards the desired demographic, but you see it's still far from a perfect correlation. So models still are very biased, even if you use those kind of personas. It's very hard to predict the extent to what this kind of steering actually has an impact, and in some cases it even has a negative impact, right? So, and for those reasons, my personal understanding, and many social scientists see it differently, but my personal understanding is, of course, LLMs are biased. I think that's still widely accepted, but consequences of that is also that the provenance of those responses are very intransparent, right? Because you have lack of transparency about the data as well as the model. And for those reasons, LLMs, from my point of view, are not a very good choice when representativity and provenance actually matters. So when you really want to draw a conclusion about people and human behavior. And for those reasons, access to data that is still very crucial in order to understand language models that were trained on that data, and in order to train our own models and methods, of course, and to eventually also mine opinions from actual data rather than opaque black boxes. And so that's a very widely debated topic overall. And to my personal surprise, very often the people were very skeptical about using social media data, for instance, to mine opinions, very often because of representativity problems, which of course are very true issues, are often the same people who now jump on this topic of using LLMs for the same kind of task. And I see that very problematic because their representativity is even worse and understanding representativity is even worse. So next to those different kinds of uses of AI and LLMs, there are, of course, many other things happening right now in research with respect to LLMs. And one infamous example was that ACL paper that was accepted this year into the ACL conference, so basically the top NLP venue internationally. And after acceptance, the authors claimed that the paper was actually autonomously created by AI, meaning they were saying the AI was actually doing literature review, identifying the research gap, designing experiments, running experiments, and actually writing the paper. And they were only dealing with slight formatting and polishing and the like. So the paper got retracted later on because, of course, there are many reasons why that's not, or why that raises ethical questions and the like. And I also believe that there's lots of overstatement and BS involved in that, because in the end that paper was basically conducted and done by an AI startup that, of course, wanted to attract some attention for their own AI models. However, what's really happening is that there's, of course, a very real wave of research investigating AI capabilities to actually do all those things, right? To identify state-of-the-art or research gaps, to reproduce research code, to replicate research. There have been, just in the last few weeks, some interesting tools. If you look at conferences like AAAI or ICLR, they have been probing with LLM-based peer reviews. So there's lots of stuff happening that's very quickly changing the way how science and research is conducted in general. And also in the computational social science field, of course, people have been turning a lot towards larger models, right? On the left, you see model performance or a plot from a paper that's been investigating model performance on hundreds of different benchmarks and averaging that performance. And unsurprisingly, larger models, of course, perform better, what also means less transparent models, and very often also proprietary and commercial models perform better or tend to perform better on average on those kind of benchmarks. And we see that in the social sciences, so that's the plot on the right. People have, of course, also been turning a lot towards commercial models. So that's a plot we generated ourselves by mining the entire corpus of AAA ICWs and publications since the last roughly 15 years. And you can see that, of course, transformer-based models have become a very general tool and means since many, many years. And more recently, of course, also people have been using a lot things like ChatGPT, what raises serious problems with respect to reproducibility as well. So that brings me to reproducibility in general and what the situation is in computer science and AI. And in computer science, or let's say in general, there have been many studies in many different fields and also surveys across researchers across many different disciplines where yeah, roughly 90% agreed that there is a reproducibility crisis in different disciplines. In computer science, the experimental apparatus is basically our compute environment. So we don't have humans involved, or in most cases at least, and things are much more binary, and to that extent, a fair assumption would be that we have better controllable variables because if you compare it to sociology or physics or biology, you have variables like weather, climate, temperature, humidity, the mood of your study participants, and all of those kind of things. And normally we don't have that. And one could assume that reproducibility is much, much easier in computer science, but if you look at the studies and numbers, it's actually not looking like that, right? So there were studies that were investigating that roughly 60% of computer science papers could be successfully replicated. But, and I think that's a very important number, only 4% by looking at the papers alone, right? So you could replicate many, many papers if you involve authors and have the chance to resolve open questions. But if you only look into papers alone, the number is very, very small. And that is a hint that we seem to have a problem with the underspecification of methods and experiments that is not typical for other disciplines, but very typical for computer science. And we also see studies that investigate those numbers and specifically what the impact of AI and deep learning based models in that context has been, right? And there has been a very interesting Best Paper Award winner at Rexis in 2019, which is called A Varying Analysis of Neural Recommender Approaches. And what they have been doing is they've been taking top-end recommender papers from the top tier conferences that publish those kind of papers. So specifically top-end recommended papers, meaning papers that actually use deep learning for those problems. And so basically they had papers, 18 papers coming from KDD, Rexis, SIGIR, and dab, so very prestigious conferences. And they followed a very meticulous protocol where they tried to reproduce those papers. They even involved the authors, tried to resolve open questions, gave them months' time, and so on. And eventually, even after following that very meticulous protocol, they could only replicate 7 out of 18 papers. So that's already part of what's worrying. What's also worrying is that with those 7 remaining papers, they did another investigation, which was trying to answer the question, do those new deep learning based top-end recommender systems actually beat very simple baselines that have been around in the recommender field since many, many years? So they had a range of different very simple baselines like this top popular or KNN based baselines and the like, and they compared performance on 3 different data sets for each of these models. And what you see in those tables here is basically for one of those 7 models, the comparison to those different baselines. And they found that only 1 out of those 7 papers or models was actually able to beat those very simple baselines, right? So in some cases, like at the bottom here, you see that even very naive approaches like taking the most popular item in general always is still better than these deep learning based approaches. So basically what they find is that a vast amount of models is actually not reproducible. The other one, or what's remaining very often, is not beating the state of the art, meaning we do have a reproducibility crisis, but also some kind of state of the art crisis because you can't trust that what you find in those papers actually is state of the art. And there are many reasons why we have situations like that, and I have yeah, very strong viewpoints on that, which I'm happy to discuss a bit later on as well. So reproducibility, of course, is not everything, right? So in machine learning and computer science, we also talk about other notions, right? So reproducibility is, of course, a very important one. Replicability and robustness are very important, and generalizability. So basically, the question to what extent models also perform when being applied to out of distribution data or data coming from other distributions is a very important, but also very often overlooked kind of notion as well. So one example here why I believe that's also a very important problem comes out of a WebConf paper 2 years ago, where researchers were looking into benchmark corpora that people were using to evaluate Twitter bot detection methods. Twitter bot detection, also for social scientists, is a very common problem. When you take Twitter data, you very often may want to eliminate data that's coming not from humans, so you have to detect what actually is a human, what is a bot, and that's the problem here. So they took existing state-of-the-art data sets that have been used very widely to benchmark bot detection approaches. So basically each row here is one of those data sets, and they trained very simple decision trees on those benchmark corpora, and they checked what kind of performance they would be getting. So that's what you see in that SDT, so that stands for shallow decision trees column. So where performance is not too bad, and you see on the right side, this delta is basically the delta between what you get out of a very simple decision tree compared to deep learning-based state-of-the-art models. And you see the difference in many cases is very negligible, so not very strong, right? And if you look closer at how those decision trees actually look like, you get a better understanding why that is and what may be potential problems with those benchmark data sets. So those are example decision trees coming out of these models that were trained, right? So on the left side, you see that on one corpus, you basically could, with those two decision trees, ever tweeted the word earthquake or liked more than 16 tweets, make a decision whether something was a bot or a human. And on the right side, that's the decision tree for another data set in that corpus or in that set of benchmark corpora, which was basically asking whether the account was created after November 27, and if yes, if if it was following more than 508 accounts. And simply based on those kind of questions in very simple heuristics, you could already solve that problem with very high accuracy. And that's, of course, not a realistic decision tree with which you can build models or decide on real world data whether something is a human or a bot, but those are very nice examples for shortcuts in the data, right? So basically, when they constructed those benchmark data sets for reasons, they ended up with those kind of very simple shortcuts that probably reflect a bit how the data was composed, how they sampled, how they annotated, and the like. And that is a very typical problem we see a lot with benchmark corpora that are used in order to evaluate AI models, right? So benchmark data very often does not represent real-world data or problems, but contains those kind of shortcuts. I think there are many obvious reasons for that. That's also true for many of the benchmark data sets I personally have been working on in the past years as well, because it's very hard to eliminate those. Some are worse than others, of course. And this kind of shortcut learning is very widespread and leads to very poor generalizability, because if you have a corpus with that kind of shortcuts, and if you train a model, then the model learns those shortcuts because that's the most efficient way to solve the problem. And those kind of learnings may be reproducible, but they are not generalizable, right? So you cannot apply a model trained on one of those benchmark corpora and apply it on real world data and assume you get the same kind of performance, because that's simply not the case. And to that extent, I really believe benchmarking is a very hard problem right now. And if you look at the state of benchmark data sets, in many cases, you will find similar problems. And I really believe, since benchmarking has such a dominant role for computer science, I believe that is a very critical problem we are facing at the moment. So that brings me to basically three different kind of areas on which we are currently working on in order to find solutions and address these kind of problems. So one is or ways on how to empower researchers to actually find state-of-the-art methods, and that includes, of course, addressing this kind of benchmarking and state-of-the-art issues I've been referring to. The second one is improving the interpretability of scholarly reporting. So that's referring to that reporting problem I've mentioned when it comes to computer science or computer science-based papers. And the third one is ensuring data availability and data access, because specifically for reproducibility and also for training models, that's of course a very, very fundamental problem. So let's start with the first. So if you look at how people currently find state-of-the-art methods for a specific task in the computational social science field, but I believe that's true in many other areas as well, even for computer scientists, what we do is we either review literature. That's, of course, very labor intensive. Models are very often poorly cited, so you really have to do lots of reading and decision making yourself. We often use code or model repositories like Hugging Face or GitHub. And what you find a lot is also specifically in the CSS field, people use what they know and what they're familiar with and what they've seen other people using, whether that's the best method or model for their problem or not. That doesn't make a very big difference. So these are not very optimal ways, right? And in computer science, we have that whole approach of using benchmarking in order to identify what is a good or a bad model, right? So we use standard evaluation corpora metrics to compare performance and quality. And in theory, a benchmark assesses whether a published method is a good or bad or state-of-the-art model or method. And in practice, as we've seen, there are, of course, many problems such as baseline choices or poor baseline choices and shortcuts in the data that make it very hard to apply benchmarking properly to get a realistic understanding of what is actually a good model or method or not. So those are things we're trying to address. And with respect to the first problem, one kind of infrastructure we've been working on and that brings together many of those things we are working on right now at the moment is called Methods Hub. And that's something for those familiar with Hugging Face, you can basically think of it like a Hugging Face-like portal for computational social scientists. It's basically a platform where you can find, share, use, and also execute data science and AI methods. The key idea is really to empower social scientists with and without technical expertise to use even complex state-of-the-art methods, whether that's simple data preprocessing scripts or foundational models for whatever kind of purpose. It contains GIS's curated methods and tutorials, but also we basically acquire methods and tutorials from the community. This kind of community method acquisition is a process that just started because it's a pretty fresh infrastructure we just released a few months ago. And most of those things are still heavily work in progress. But the key idea is really that we introduce ways on how to make things more reproducible, so good documentation, that methods get a DOI so that you can cite methods and models in the same way as you would cite a paper or a data set, that there's some kind of quality curation, that there is a documentation that also makes it feasible for less technical people to apply those methods. And of course, we also are currently working on introducing benchmarking protocols, benchmarking data sets, and benchmarking results into the platform to make it easier to compare methods or different methods on the same task and problem. So when it comes to benchmarking, there's one example on how we are currently trying to establish more realistic benchmarking habits. And one is, for instance, research coming out of that paper where we've been evaluating the generalizability of NLP models. In that very case, NLP models that address the task of argument mining, specifically in social media posts. And so that's addressing the task that is shown in that table here. So you have tried to discriminate statements or sentences that are arguments, like the top 3 kind of examples that come out of different benchmark data sets for that problem, from sentences that are no arguments. And there's a wide debate going on of what actually is an argument, but leaving that aside, there are tons of benchmark data sets. It's a very established NLP task and very established NLP problems. And what we've been doing was collecting all of those benchmark corpora that we could find that address that task. And based on some kind of criteria, we selected the ones that we deemed most relevant and most important. These were 17 different data sets, and we started conducting some experiments, taking state-of-the-art models that were successfully used to obtain state-of-the-art performance on any of those benchmark corpora. And we trained them on one corpus and basically tested on another corpus. And that's what you see in that heat map here. So if you look at the diagonal, it's basically the trained and testing on data from the same distribution, basically from the same data set, where you see it gets a bit darker because performance is not that bad actually. But as soon as you go left or right from the diagonal, you see that in some cases performance gets even pretty random, right? So pretty close to chance, since that is a binary classification task, of course. Values that are in the 50% or 60% range are not really good values. And so what we see here is that performance degrades when models are tested on this kind of out of distribution data, which already gives us a good hint that many of those models may contain shortcuts that have nothing, or many of those data sets that may have nothing to do with the actual task that we want the model to learn. And we did another experiment where we said, let's give the model basically all the data we have, all the data from all the data sets. So just not the data set on which we tested, right? So basically, if you go to one line, like this AAC line, the model that has been evaluated here was trained on 16 data sets, just not the AAC corpus, but all the others, and it was tested on the AAC corpus. And one assumption could be, hey, the model has seen so much different data, it should do a pretty good job even when tested on out of distribution data, but that's really not the case, right? So you see here the bold SOTA column here, that's basically the SOTA performance, the state-of-the-art performance when being trained and tested on the same data set. And if so, that was 96% here. And with our experiment where we trained on 16 data sets, but not the AEC corpus, performance degraded dramatically, right? And that is, I think, also very typical for data sets that are not strong and that may contain lots of shortcuts, that they are also very easy to learn because you have nice shortcuts. And if you train and test on that model, you get very good performance. But specifically, the ones that seem easy to learn are the ones that also don't have a very good generalizability, right? So that's exactly what we see here as well. So we did many more things, also trying to train models that generalize better, but we also think it's very important to engage with the community, to also establish better benchmarking protocols that really value specifically generalizability and evaluate also to what extent models actually generalize across different kind of or more diverse data distributions and data sets. And that's something we do, for instance, at the CLE initiative, where we run several evaluation initiatives where we basically work with the NLP and IR community in order to establish those benchmarking protocols as well. And the idea is also that models that are being developed as part of those shared tasks and challenges are being shared within the Methods Hub together with those benchmarking results as well. So that brings me to the interpretability of scholarly reporting, right? So the reporting problem that I've mentioned is also a very crucial problem when it comes to reproducibility as well. And one underlying cause for that is basically that the primary documentation of scientific output that we have is still unstructured publications. So that's a ChatGPT impression of how a publication looks like. I think it's pretty close to how the papers I print out also look like. And there are, of course, many issues with that kind of representation of scientific results, right? So one is, for instance, papers very often have very informal citations of data sets or computational methods or code, right? So PIDs are not really consistently adopted in scientific publications. Very often you also find broken citations, ambiguous descriptions of data sets or method adoption. So for instance, problems like sampling methods that are not very well described, and very often also training procedures for machine learning models, for instance, training and test splits of data sets and the like, are not very well specified. So these are all kind of problems that, of course, could be addressed and could be improved. And what is a very common tool, what people are using a lot right now at conferences, for instance, at ACL and NeurIPS, are these kind of checklists. Right? So when you submit to those conferences, you're forced to complete these kind of checklists that question many things that may have impacted reproducibility in your paper. And that's exactly one of those things we are also working on. So surveying with social science and computational social science researchers, what are actually their struggle points and challenges when it comes to reproducibility, and working out checklists that we can establish in the social science community that they can actually produce research that is easier to reproduce in the longer term. So checklists are basically one of those things where we try to make research before it's being published already better and more reproducible. But on the other hand, of course, we do have millions of research papers that are already published, and we have to make sense out of these, right? And there's another kind of approach we are following here, which is trying to mine scholarly papers, for instance, for information that is crucial for reproducibility, such as information about machine learning models, data sets, tasks, metrics, and the relations between those things. So if you look at that sentence on the right, that comes out of an ICWSM paper, and in an ideal world, we would like to have data sets being tagged as such, tasks being tagged as such, machine learning models that I mentioned being tagged, and basically being able to mine all of that information and also use it in order to create large knowledge bases of, for instance, machine learning models, how they were used in different tasks and on different data sets, what the relation between all of these things is, to make those things more researchable and easier to use. And that's exactly what we've been doing, right? So basically creating models that are addressing that task of mining papers for this kind of entity types. And we've done that by annotating publications, right? So we have a corpus of 54,000 mentions of those kind of entity types, and we fine-tuned language models using that kind of corpus, and basically conducted some experiments on the performance. And we also applied that on larger corpora. Currently, for instance, we are working on the entire ACL anthology as well in order to make sense out of those communities. So this is a performance plot of those models. You see that the Psi-Liberta model, for instance, trained on or pre-trained on computer science literature, works best because we also have applied it to computer science papers as well. And you see that performance is not excellent, right? But on some of those entity types, it's actually not bad. For instance, for tasks, or for tasks not, but for data sets, it's working quite well. What is interesting is that this performance variance also correlates a lot with the inter-rater agreement. So if, for instance, there are specific relations or types where the models struggle to detect those things, it's very often the kind of stuff also humans struggle to detect, simply because it's not described and referred to very well and explicitly in those papers. So it gives us a hint also about quality of computer science literature. And this is basically the output of that model. When you look, for instance, at tasks and methods, that's what we got out of mining the entire AAAI ICWSM literature. So simply based on the plots I've been showing beforehand also. So there you can, if you apply that on larger corpora, you can nicely analyze, for instance, how the model adoption in a specific research field has been changing over time, like what you see on the plot on the left. And for instance, also how the adoption of different data sources has been changing over time in a specific community, where you see that, for instance, on the right side, people, of course, have been using Twitter a lot in computational social science research. If you would continue that plot, of course, the Twitter adoption would go down dramatically, since we have a problem with Twitter data availability right now. But you can basically try to better understand the evolution of reproducibility habits of entire communities and disciplines using those kind of techniques. And that's what we're also working on right now. And we've also published a tool that basically gives you also the chance to analyze your own PDFs and papers. So they can basically upload PDFs, and then you get for each paper or for a bunch of papers the extracted information about what are data sets being mentioned. You get for each of those entity mentions we find in that paper also the sentences being shown, and you can basically analyze and mine papers according to your own liking. That's actually publicly available. I didn't put the URL here because it's not we are highly scalable yet. The infrastructure underneath is still a bit too shaky, but we are currently working on making that more robust so that it can really be used by a larger audience as well. And again, also on those kind of problems like mining scholarly publications for that kind of information about data sets or models or software mentions. We are also running shared tasks with the community. We've done that at ACL and at ESWC a few years ago. I think we are currently doing that at LREC next year as well. And basically for all of those problems, we try to engage the community in order to work on addressing those problems, which we believe are quite fundamental. And now I come to the last part, and I think I'm only going to show one slide for that because we are running out of time, and I think it would be good. It would be good to have some time for discussions as well. So I've mentioned data access being a very crucial problem as well. There are many reasons why that is, and why data availability has become a very big problem, and why getting data and being able to use data is still very problematic. And we see that GESIS has a very important role to play in order to ensure data availability for the research community, whether that's in the computer science area or in the social sciences. And for those reasons, we are working on responsible social media archiving since many years. And with those activities, we're basically trying to make platform data coming out of very large online platforms, whether that's Telegram or fact-checking sites or Twitter or X or Blue Sky. We are trying to preserve that for the research community and trying to find ways to make data accessible in a responsible, less sensitive way for the research community as well. And if you go to these URLs, you will find some information about those data sources. I think one of the more prominent examples is our Twitter corpus, where we've been basically harvesting a 1% random sample since 2013. So it's basically a complete and continuous sample of 1% of all tweets that have been published in this 10-year time period, consisting out of 14 billion tweets. And we are currently doing similar things for other platforms in order to facilitate research, facilitate researchers who want to train their own models on using data sources coming from any of those platforms. And we believe that's a very important topic. So let's come to the wrap up, right? So I try to focus on first motivate, and then also try to explain some ways on how better method quality and reproducible could be achieved. And one is, for instance, by making or finding ways to find methods and understand the state of the art better through better benchmarking practices for infrastructures like the Methods Hub that is meant to curate and document method quality, benchmark results, and the like, and to engage the community in those kind of benchmark activities, for instance, for shared tasks. The second part was referring to this whole problem of reporting quality. So how can we, on the one hand, incentivize better reporting habits so that people, for instance, use persistent identifiers more consistently, address fundamental reproducibility problems in their papers, but also how we could mine existing papers in order to better understand method adoption, better understand dependencies between methods, tasks, and data sets and the like. And the third part was referring about data access, right? So how we can better archive data for the research community, can become independent from gatekeepers such as the big tech companies that are currently the gatekeepers for much of the data we actually need to use and want to use, and how we can find ways to securely access data sets like that, and how we can create actually the legal conditions for the safe use of this kind of web data methods. And I believe that these are all problems that really require some kind of culture change across communities, and of course, specifically also in the computer science community and everyone who is working with us and working with computer science methods. And to that end, I think it's also a very interdisciplinary effort. And with that, I'd like to say thank you for listening. And of course, also thanks to all the people in my team. That's a not very up-to-date picture, but I hope no one is in the audience who can complain today. So thanks a lot. I'm very happy to take questions.